why compensation is required. Okay. See, sometimes it happens the system is unstable. Okay. So in that case we need to make some provisions to make it stable. So what we do, we put some compensators, either lead compensators or lag compensators. Sometimes the desirable output coming from the system is not the correct. So to maintain that, we again need compensators. Okay, so compensators are just basically a technique to get a desirable output. Okay, so what are the various type of compensators? The first one is lead compensators. Second is lag compensators. Third one is lead lag compensator. What is leading in lead compensator? What is lagging in lag compensator? See, the term which is leading in lead compensator is phase. The term which is lagging in lag compensator is again phase. In lead lag compensator is again phase. Okay, we will see under certain frequency range it is leading, under certain frequency range it is lagging. Okay, we will cover the first one, lead compensator. If I draw the S-plane representation of lead compensator, S-plane representation of lead compensator is something like this. In this, 0 is near to origin, pole is away from the origin. Q omega axis signal minus Zc equal to minus 1 by tau, some constant, minus Pc which is pole of compensator, minus 1 by alpha tau. Okay. Now, transfer function of compensator is S plus Zc upon S plus Pc. Okay, so in terms of tau and alpha, I can write it as S plus 1 by tau upon S plus 1 by tau alpha. Okay, this can be written as alpha outside S plus S tau plus 1 upon 1 plus alpha tau S. So this is a transfer function for the compensator. Okay, now we look physically how this compensator will look. That means the electrical representation, electrical component wise representation of these compensators. The combination of resistance and capacitance can make this compensator. Lead network. This is my lead network, V in, this is V out. Okay, in this case alpha is equal to R2 upon R1 plus R2 and tau is equal to R1C. Now in this case if we see the phase of this, it will always be greater than 1. See. Considering the sinusoidal transfer function, Gc of j omega is equal to alpha times of 1 plus j omega tau over 1 plus j omega alpha tau. Alpha value is lesser than 1. From here alpha value is always lesser than 1. Okay. Now I can find my phi is equal to tan inverse omega tau minus tan inverse alpha omega tau. This gives me tan phi is equal to minus omega tau 1 minus alpha 1 plus alpha omega square tau square. To find the maximum phase, d phi by d omega is equal to 0, because we have to differentiate with respect to frequency. Once we differentiate, let this be equation number 1. If we differentiate equation number 1 with respect to omega and equating that equal to 0, I will get some omega m is equal to 1 by tau root alpha. Okay. Also equal to 1 by root tau 1 by root alpha tau. Okay. Now we'll find the phase at omega equal to omega m. Substituting omega m, one by tau root alpha in tan phi, I will get tan phi m is equal to 1 minus alpha upon 2 root alpha. Okay. Or sign, much simpler expression for this is 1 minus alpha upon 1 plus alpha. Okay, so this is a magnitude, this is for the phase, magnitude of jc j omega m 1 plus j omega m tau 1 plus j alpha omega m tau, so 1 by root alpha. This is the magnitude. So we have seen the phase, which why it is called a lead compensator. Okay, the phase is always positive. Write a note. Phase in lead compensator is always positive. Okay, alpha value is always lesser than 1. 0 is near to origin, then pole. Okay, next the Bode plot. The Bode plot of phase lead network. In this, if we plot the magnitude plot, since there are 2 points, g of j omega, this is in dB. Okay, so now up to first point 1 by tau, this is one cutoff frequency at which magnitude will close to 0. Okay, then after this point magnitude will keep on rising. Because of presence of 0. Okay, and after this point it will, it is changing at a rate of 20 dB per decade. This point is 1 by alpha tau. Okay, at 1 by tau there is a presence of 0, so this will start increasing at a rate of 20 dB per decade. At 1 by alpha tau there is a presence of pole, so presence of this presence of pole will compensate for the presence of 0. So 20 dB per decade is increasing. At pole, after pole it will decrease at the rate of minus 20 dB per decade. So net rate of increase is 0 dB per decade. So it will remain constant after that. So this is a magnitude plot of this. Now we will see the phase plot. Phase plot. By looking at the phase plot, this is 0 degree, this is 45 degree, and this is 90 degree. Zero, one pole, okay. The phase will increase somewhere between these two. That means at the phase will be maximum. After this, it will again decrease. So this omega m is nothing but geometric mean of 1 by tau 1 by alpha tau is equal to 1 by tau root alpha. This is the phase plot. Okay. So this is the thing which is required for lead compensation. Okay. So now we put this lead compensation before any system. Lead compensator. System transfer function. Now the phase response of this complete system will have addition of this phase. Okay. So this is lead compensation. Next we will see lag compensation, or second one is lag compensator. Now we will see the things are totally reverse in this. First, S plane representation of lag compensator. Okay. The S plane representation of lag compensator is just reverse of the lead compensator, j omega sigma. In this, pole is near to origin and 0 is away from the origin. Beta value is always greater than 1. Okay. Finding the transfer function of this. S plus Zc upon S plus Pc. I can write S plus 1 by tau upon S plus 1 by beta tau. Okay. Realizing the physical lag network form of electrical components is something like this. Okay. Beta in this case is R1 plus R2 upon R2, which is always greater than 1. Tau is equal to R2C. Okay. So this was the physical network and things explaining R, beta and tau. Now looking for finding the phase, we have to consider the sinusoidal transfer function. When I say sinusoidal transfer function, it means that I am writing my transfer function only in terms of j omega. Okay, phi in this case is tan inverse omega tau minus tan inverse beta omega tau. Now in this case phi is always negative because beta value is greater than 1. And phi is this. Now to find the maximum value of phi, we have to differentiate this function of phi with respect to omega. On differentiating, finding d phi by d omega and substituting it to 0, I will get frequencies 1 by tau root b, okay, which is nothing but the geometric mean of pole and 0. Next, sin phi m is you will get by substituting omega m, which is equal to 1 minus beta upon 1 plus beta. Sin phi m is always negative, so phi m is also negative. Okay, so if we look at the body plot and body plot for plotting magnitude plot and phase plot, I have pole first. So once there is a pole, after that I will have a slope of minus 20 dB per decade. Okay. After that, pole at 1 by tau, 0 at 1 by tau will add a slope of plus 20 dB per decade, which will make a total slope 0 dB per decade. Okay. From 0 to this point, the value is 20 log beta. Omega m equal to 1 by tau root beta. Similarly, plotting the phase plot. Phase plot is always negative in this. In lead, it is always positive. In lag, it is always negative. Okay. 1 by beta tau, 1 by tau, 1 by tau root beta. We have some maximum value somewhere here. Maximum value is always less than minus 45 degree. In earlier case it is in lead it is always greater than 45 degree. In lag it is always greater than minus 45 degree. In lag it is always less than minus 45 degree. That will be more negative. Phi m is the maximum phase. Okay. So these are the important things about the lag compensator. Now the third one which is left is lead lag compensator or lag lead compensator. Third, lag lead compensator. Just understand the S-plane representation of lag lead compensator. Okay, there will be a pole near to origin minus 1 by beta tau 1. There will be a 0. This will corresponds to lead part. Then corresponding to lag part, I have 1 minus tau 2 here, and pole much farther away from the origin, alpha tau 2. Okay, beta value greater than 1, alpha value lesser than 1. If we look at the transfer function of this, s plus 1 by tau 1, s plus 1 by tau 2 upon s plus 1 by beta tau 1, s plus 1 by alpha tau 2. Okay, now physical realization of this is lead lag network drawn like this. R1 C1, R2 C2. Okay, this is a physical realization of lag lead network. So in this network, tau 1 is equal to R1 C1, tau 2 is equal to R2 C2. Okay, R1 C1, R2 C2 is equal to alpha beta tau 1 tau 2. Okay, this gives alpha and beta should always be equal to 1. That means alpha and beta are inversely proportional to each other. From the network, if I write the equation of V naught S by VIS, I will get S plus 1 by R1 C1, S plus 1 by R2 C2 upon S square plus 1 by R1 C1 plus R2 C1 plus 1 by R2 C2 S plus 1 by R1 R2 C1 C2. Okay, no need to remember this, it is just for understanding. Bode plot. Okay, in this first, the magnitude plot. If we look at the magnitude plot, I have pole first. Okay, 1 by beta t1. After that pole I have 0. Again I have one more 0. Then I have pole. Okay, so if I have a pole here, it will decrease at a rate of minus 20 dB per decade. On reaching 0, it will become 0 dB per decade. Again one more 0 is there, it will become plus 20 dB per decade. Then on reaching pole it will become 0 dB per decade. Presence of 0 will add a slope of plus 20 dB, and presence of pole will make a slope of minus 20 dB. Okay, this amplitude of from here to here is equal to minus 20 log 1 by b. Okay, or it can be written in terms of alpha minus 20 log alpha. Now plotting the phase plot, since it is a lead lag, so some portion of phase plot will be negative and some portion will be positive. Okay, so again 1 by beta tau pole, 1 by tau 1, 1 by tau 2, 1 by alpha tau 2. Okay, so first there is a lag compensator. So since it is a lag, so phase will be decreased. Then it is a lead compensator. So it will increase and it will become like this. Okay, so here it is a lagging part, here it is a leading part. This is a phase plot of this. Some at various places lead lag compensator, that means combination of lead plus lag is used. So this was this topics regarding the compensator. Okay, we have seen the lead compensator, we have seen the lag compensator and lead and lag compensator. We have seen the frequency at which phase is becoming maximum. We have also seen the frequency, we have also seen the maximum phase, we have also seen the minimum phase in case of lead and lag compensators respectively. We have learned about the phase lead, phase lag and phase lead and lag compensation. Okay, now we will see the effect of phase lead compensation. Okay, the first one in this is it increases the gain crossover frequency. Okay. Phase margin is increased. And hence bandwidth of the system also increases. Third one is speed of response, that is how the system is responding, that speed is increased. And the overshoot is reduced. Fourth one is order of a system is increased. Okay, it acts as a what? High pass filter. Why so? If we look at the response of this, then it is something like this, which is allowing the frequencies only after certain interval of time, not the lower frequencies. Okay, that's why it is a high pass filter. Steady state error improves detail. Improvement in steady state error is not much. Okay, only This system increases the gain crossover frequency, which in turn increases the phase margin, and thus the bandwidth is increased. Okay. So these are the effects of the phase lead compensation. The question can come as a 1 mark question from any of these effects. Okay. Next will be the effect on the effect of phase lag compensation. Effect of phase lag compensation. Okay. First one is the gain crossover frequency reduces. Thus bandwidth is low. Okay. Time constant of a system is increased. Thus the time constant is increased, system becomes slow. Okay. Third one, steady state error is reduced. Okay. Fourth one is open loop gain increases but system is stable. These were the effects of the phase lag compensation. Okay. So this is also can also come as a 1 mark question in the GATE exam. Okay. So this completes the topic of compensation, the phase lead, phase lag, and phase lead and lag compensation. Now the effect of phase lead and phase lag compensation are nothing but clubbing these two effects. It comes in overall the trade-off between these two. Okay.